Thank you. Thank you very much for the introduction. Thanks everyone for tuning in, and welcome to lecture 6 of this ongoing series on DeCifrisTrends and cryptographic protocols, which is sponsored by the University of Trento and by the componentis Cifris. Okay, so in today's lecture, we're going to talk about fully homomorphic encryption, and I'm Professor Daniele Venturi from Sapienza University of Rome, where I'm affiliated with the computer science department. Okay, so I try to, so the goal is to introduce fully homomorphic encryption. Of course, before doing that, it's good to refresh our ideas on public key encryption. So in public encryption, Alice wants to send a message to Bob over an insecure channel, which is completely controlled by the adversary. In particular, the adversary can read whatever is sent over the channel, and then she does so by means of a public key encryption scheme as follows. There is an algorithm which takes as input the message and the public key and outputs a ciphertext C. And this ciphertext C is what Alice sends over the channel in such a way that Bob can use the corresponding secret key SK, which corresponds to PK, along with the ciphertext that he receives from the channel in order to recover the message M. Okay, so in this concept, was like a kind of like big revolution in cryptography, and was proposed originally by D.F. Hellman in the seminal paper New Directions in Cryptography. It was around the 70s because it was the first proposal for achieving message confidentiality without Alice and Bob sharing a key first. Okay, so like talking over a public channel without sharing a key beforehand. And the first realization of this was based on the hardness of factoring, and this is like the basic and very famous crypto system by Rivest, Shamir, and Adelman 2 years later. Okay, and then since then, like many new realizations of public encryption are known, and in particular, when we talk about security, it's actually important to like give a quick note about what we mean by a secure public key encryption scheme. And typically the standard notion of security, or maybe we should say the minimal notion of security, is the so-called chosen plaintext attack security, sometimes known as CPA. And this can be understood in the following way. We consider an adversary, Eve, and a challenger, okay, which is the cat in the slides, and they play a game. Okay, so the game goes as follows. The adversary knows the public key, okay? And the public key is generated by the challenger along with the secret key. Okay, so you can think of this public key and secret key as the keys of Bob, for instance. And now the adversary picks any two messages x0, x1 of the same length, and it receives the encryption C, which corresponds to either x0 or x1, say xb, where b is chosen with probability 1/2. Okay, so like with flips a coin, if it is tail, encrypt x0, if it is head, encrypt x1, give the ciphertext to the adversary, and now the adversary has to decide whether it was an encryption of m0 or an encryption of x0 or an encryption of x1. Okay, and then the adversary would be successful. The adversary will be successful. He could guess or he could understand which message was encrypted with probability significantly better than 1/2, which is of course like always possible because the adversary could just guess. Okay, and in particular, an encryption scheme is instead secure if no adversary can do this. And so this kind of notion, which is like looks like kind of abstract and detached of reality, it was established in the early days of cryptography, that indeed corresponds to like very strong security guarantees for public key encryption. Okay? So in particular, this definition implies that the adversary cannot guess even a single bit of the plaintext. Okay, so like really the ciphertext hides all possible information about the plaintext. And the reason for this is because the messages are adversarially chosen. Okay, so like the adversary could know everything about the messages but 1 bit, and still it should not be able to tell which message was encrypted. And as a sanity check, you can like very easily see that this notion implies, for instance, that it's hard to recover the message, also hard to recover the secret key. Okay, so moreover, like in the early days, it was proven indeed that this definition is actually equivalent to much more complicated definitions. We try to capture all details of a real execution of the protocol between Alice and Bob. Okay, so I take this as granted that this is a standard notion, and then let me actually bring the main question, which is what we want to talk about today, and this is the question of how to compute over encrypted data. Okay? So in particular, the question is, can we have a public key encryption scheme which allows to run computations over data which is encrypted? It's like a very old question dating back to the 70s. In fact, it was like asked first by Ron Rivest under the name of privacy homomorphism. Okay, and then first of all, as a sanity check, I mean, like just to understand what kind of question this is, notice that in fact, like partial solutions to this question were already known since the early days of public key encryption. So like, for instance, RSA itself, or like El-Gamal, which are like very basic CPA secure public key encryption schemes, they directly enjoy limited forms of homomorphism, where homomorphism here means like I can take two ciphertexts and I can, for instance, multiply them, and then I don't know what's inside. I get a new ciphertext, and this new ciphertext, if I decrypt it, I get like the product of the plaintext. Okay, so even though I don't know what the ciphertext encrypts, I know for sure that it's going to encrypt the product of the plaintext. So this is also, you can think of this like also as a form of malleability, which could be like either good or bad depending on the application. And well, for some applications, it's actually really good. Okay, so and the main question was like, can we have like an encryption scheme, like a public key encryption scheme, that would be able to support arbitrary homomorphism, okay, not just product or addition, but like, I don't know, like any computation over the encrypted data, just fix like some whatever model of computation and have an encryption scheme that supports that model of computation. Okay, and this was like a kind of the holy grail of research for public key cryptography for a long time, since its invention, and it took 30 years before it was solved by Craig Gentry, where he defined is like a new fully homomorphic encryption scheme using ideal lattices. It was like a paper at Stock 2009. And so this solution was like a very complicated and based on kind of new assumptions, but then like it was also groundbreaking because it kind of gave a blueprint how to construct fully homomorphic encryption, which is what I want to try to tell you about today. And then since 2009, actually a lot of progress happened. And in particular, we improved very much our understanding of how to construct fully homomorphic encryption, in particular using assumptions which are far more standard than the one that Gentry introduced in the original paper. And also, this will be the focus of today's talk. Okay. And then, I mean, once FHE, fully homomorphic encryption, became available, like people started to explore, like, what can I do with it? Okay, and for some time, this has been known as the Swiss Army knife of cryptography because, you know, since when it became possible, whenever you have like a crypto problem that you don't know how to solve, you just try to solve it with fully homomorphic encryption because this is very powerful and also possible now. Okay, so, and indeed, let me give you like such an application, okay? So such an example of application where fully homomorphic encryption comes handy. So this is the problem of outsourcing of computation again. So the idea is like you have Alice, and Alice runs some small computational device, okay, like a smartphone. So she doesn't have so much computational power, and she would like to compute like some complicated function of its input. Okay, so it's like some input x, and she would like to compute f of x. But this smartphone is like is not very powerful. So this would be like too much time consuming. And so what she does, like she outsources the computation of the function to the cloud, okay, to some server in the cloud. And now the cloud has like lots of computing power. In fact, like can offer this service to multiple clients. And then it gives back to Alice f of x, okay, where f is like think of it as like some public function. Okay? So like, of course, this is like very abstract, but I mean, of course, it corresponds to like real world problems. Like you can think of like a web search or like navigation, social networking. I mean, like it covers like lots of applications. But the main question, of course, here, like which makes the problem like really non-trivial is what if X is private? Right? I mean, like this X could be like private data of Alice. How can we now do? How can we solve this problem without Alice revealing the X to the cloud? Okay. So of course, on the other extreme, like Alice could do the following. I mean, she could encrypt X, right? Like she could like sample her own pair of keys, PK and SK, and then use the public key in order to encrypt X. Send X encrypted to the cloud. But now how the cloud can compute on X, right? Because this X is encrypted, the cloud is not able to evaluate on X, except if the encryption scheme is fully homomorphic, okay? And here you see what this means now. So there is an algorithm, which I call eval, as evaluation. And this algorithm is kind of like some magic algorithm that takes as input only the public key and the ciphertext, right? Plus a description of the function. Okay, all public information, like the public key is public, ciphertext is also sent over the channel, so you can think of it as public, and the function f is public. And now you run this function eval, and you get some output y, which is sent back to Alice. And now we would like the following guarantee. If Alice is gonna decrypt y, she gets f of x. Okay. So somehow this fully homomorphic encryption allows the cloud to evaluate f over the encrypted data without knowing what the data is. Okay. And of course, we would like also this scheme to be private, okay, as usual, which is like CPA security. Okay. Yeah, so encryption of x is like indistinguishable from encryption of 0, or like the previous definition is equivalent to this. Okay. The CPA security definition is equivalent to the one written in this slide. Okay, and then moreover, we would like to be like very ambitious, and we would like, in fact, to achieve this property not just for some particular function f, but in fact for every function. Okay, independently of what the function is. Okay, so like so this usually corresponds to the following. I mean, like x is like binary maybe, or like defined over some field, and you need to fix some kind of model of computation where you want to represent your function. This could be like Boolean circuits, or like arithmetic circuits, or like whatever model you like. And then you would like to have a fully homomorphic encryption scheme over that model of computation for every possible function. And of course, now this like is equivalent to actually ask whether we can have fully homomorphic encryption for a universal set of operations. Because, for instance, if you want to do Boolean operations, we know that the NAND is like a complete set of operations, right? Or like if you have a ring over some field, or sorry, if you have a ring with two operations, then like a complete set of operations will be like addition and multiplication first over a ring. Okay. And yeah, so this is yeah, what I just said. And of course, maybe we would like to be like a little bit less ambitious, and instead of working for every possible function, we could like put a bound on the depth of the function. Okay, so like say that this is a circuit, then we can evaluate all circuits of depth at most tau. Okay, where tau is some parameter. Okay, and this would be called like would be like kind of something weaker. It's not like fully homomorphic, and it's called only leveled homomorphic because it works only for certain families of functions or classes of circuits. Okay, so in order to get like some confidence with this concept, let's look at this idea of the following like trivial fully homomorphic encryption scheme. Okay, take any public key encryption scheme, okay, and define the following fully homomorphic encryption scheme. So this will be exactly as the original public key encryption scheme, except that my evaluation function does the following. It encrypts, it takes as input the public key and the ciphertext and the function, as usual, and it outputs the ciphertext along with the function. And now the new decryption, what it does, it takes as input the ciphertext, which is now the function and the ciphertext, right? And now what it does is just like apply f to the decryption of C. Okay. So and of course, like this is like completely silly, because it's like if you think about this cloud application, this means the cloud is gonna, so the Alice encrypts X, and then the cloud gives to Alice back X plus the function, and says to Alice, okay, decrypt X and compute the function on your own, which of course completely kills our motivation. It doesn't make any sense. yet, you know, it's not ruled out by the current definition that we have of fully homomorphic encryption. So in order to make the problem interesting, we need to add something on top. And in particular, we need to add like an efficiency requirement. So we want that the complexity of the decryption should be much less than running the circuit from scratch. Okay, so that this trivial FHE is ruled out. Okay, so one way to say it also, alternative to this, is to require that the dimension of the ciphertext should be compact. Okay, so like there exists like a fixed polynomial bound such that if you look at the size of this ciphertext, it is at most of size B of lambda with high probability. This should be true for all circuits F, maybe with bounded depth tau, if you want to do just leveled homomorphic, and also for all inputs to the circuit. And of course, the probability will be over the randomness for generating the key and over the computation of the ciphertext. Okay. So, and this, I mean, yeah, this completely rules out the previous example, right? Because in the previous example, actually, the size of the ciphertext grows linearly with the description of the function, because in this trivial example from the previous slide, the ciphertext includes the function as part of the ciphertext, so it's very large. Okay? So if it is compact, or like if the dimension of this ciphertext is independent of the function, then it's good. Then it's non-trivial. I mean, and in fact, like notice that it would also be non-trivial if there is like a little dependency, okay, but this dependency is still like, you know, much less than the description of the function. So it could be like, I don't know, like a little o, for instance, of the log of the cardinality of the function, which means like much less than the size. Okay, so this would still be non-trivial, even if there is like a little dependency in a way that it doesn't allow you to compute the function itself. Okay, so given that, I want to now like focus on presenting, actually giving you a construction of FHE. And the scheme that I will present is the one due to Gentry, Tsai, and Waters, which was published at Crypto 2013. And the cool thing about this scheme is that it's actually based on a very standard cryptographic problem, which is called the learning with errors problem, LWE. I'm going to say what it is in the next slide for people that don't know. This scheme actually, as we will see, only achieves leveled homomorphism. Okay, so only satisfies homomorphism for circuits of depth at most tau, for some fixed parameter tau. However, then there is a trick by Gentry that allows to bootstrap this to a fully homomorphic encryption, so no depth bound, no bound anymore. And this is actually very general, and I'll try to say something about this at the end of the talk if there is time. The only caveat is that this bootstrapping technique will require an additional assumption. So the LWE assumption alone will not be sufficient. Okay, and for concreteness, the plaintext space is going to be ZQ, integers mod Q, and I will represent ZQ as integers between minus Q alpha and Q alpha, okay, where Q is a prime. Okay, also write A sub Q for A mod Q for shorter. Okay, so let me first introduce what this learning with errors problem is. It was introduced by Regev in 2005. And this is like a very standard cryptographic problem, or like a hardness problem. And the problem can be thought as follows. Like we have the following experiment where we have a secret vector of elements in ZQ, okay, mod Q. And then we have a matrix, like a public matrix A, okay? And then we compute S times A, and we publish the result B, okay? And now the question is, can you compute S? Think of this matrix A as being like uniformly random, okay? So now the thing is, of course, that if we do this, it is actually easy to compute S, because S times A equal B defines a system of linear equations that, of course, can be solved by Gaussian elimination if the equations are independent. And this will, of course, be the case if the equations are random. With high probability, they're going to be a set of independent equations. Okay, so then how to make the problem hard? Instead of publishing S times A plus equal to B, we add noise to these equations, to each of the equations. Okay? And this is the eta vector in the slide. So we add this noise. And now the question is, what is the distribution of the noise? So yeah, the noise should be small, okay? So which means the only assumption that we're going to make on the noise is that if you look at each individual entry in the vector, then the absolute value of this entry is like much smaller when compared to Q. Q is the modulus, okay? So like is at most alpha Q, where alpha is like a small constant. And I mean, there are actually many ways how to create this noise. For instance, it could be like Gaussian, or like a discretized version of the Gaussian, right? Because this is discrete, which satisfies this property because of the tail bounds, the classical tail bounds for Gaussians. So it's like very unlikely that the magnitude of the noise is large. Okay, so we have this, okay? And now the question is, can you compute S given this system of equations? Or actually, an equivalent way to phrase this problem is, instead of computing S, I give you A and B, and can you distinguish whether A and B is computed like in the left part of the slide, or is actually completely random? Okay, so A is random always, and B, instead of computing B as S times A plus noise, I just pick it at random. Okay, so this would be like the decisional version of the problem, and in fact, the two things are equivalent. Okay, like if you can distinguish, you can compute S, and vice versa. If you can compute S, you can also distinguish. Okay, so that's the LWE problem. And what can we say about the hardness of this problem? So first of all, it's very easy to see that brute force takes like essentially like exponential time. This is like follows by Gaussian elimination, and there is an algorithm by Blum, Kalai, and Wasserman, which is kind of the state of the art, which takes sub-exponential time. So like 2 to the n over log n. But this is the best algorithm known so far. And in fact, this is actually even true even under a quantum model of computation. Okay, so like even if you have a quantum computer, we know no quantum algorithm, even idealized, that can solve this problem faster than classical algorithms. Okay. Moreover, it also has some nice like kind of complexity properties, like this worst case to average case hardness reduction, which essentially says that if you can solve like the problem for a random instance, you can actually solve it for every instance, which is like a very nice thing. And moreover, like even more importantly, people studied this problem extensively, and in fact, it is known that for some parameters regime, in particular about alpha and the modulus, then if you can solve this problem, you can solve like problems over lattices, like approximate short vectors in a lattice, which is a problem that mathematicians studied for decades, if not even centuries. Okay, so which means that this like problem is like really well-founded assumption. We really believe this problem to be hard. It's not like a new problem that we thought of yesterday. It's like a problem that is around for centuries, and that if this problem would be broken, it would be like really surprising. Okay, so let me like quickly write like an equivalent way. So before describing this fully homomorphic encryption scheme, let me like change the notation slightly. Okay, so on the left on this slide, I just have whatever I just said. So we have the LWE definition, which is SB is equal to S times A plus noise. Okay, where S is uniform, A is uniform, and eta is this Gaussian noise. And what the adversary knows is A and B, right? So now we equivalently we could do the following. Okay, like we could think of S as being S with the -1 at the end. So like just put a -1 over the S, and then merge A and B in a single matrix. Okay, so like add B as the last row in the matrix A prime, which is below A. Right? And if we do this, we get the noise, right? Because S times A minus B is equal to the noise, right? Plus minus the noise doesn't matter, right? Because anyway, there is like absolute value. So you get this, the two things are the same, okay? So we will follow this the right definition because it's like more compact. Now I can say that like a definition, like an instance of the LWE problem is just a matrix A or A prime, which I will call A from now on. And then you should think of like this matrix as being like A and then B in the last row. And then you multiply with this vector S with -1 at the end, and you get the noise. Okay. So it's just like an equivalent way to define it. So now it's more compact because I can just say S times A equal noise. Okay. And I can forget about B kind of. Okay. And then, of course, the assumption is still the same. Like this matrix A with B at the end should be uniform. It's computationally hard to distinguish this matrix from uniform. It is exactly the same problem, just like, you know, rearranging the notation. Okay, so it seems now we are ready to define this crypto system itself. And this follows like a very natural idea, which is called the eigenvector method. So the idea would be this, okay? So this was like the basic idea of this Gentry-Waters construction. Think of like any two matrices, C1 and C2, okay? And think of the standard like eigenvector-eigenvalue relation, okay? So like you have S, which is the eigenvector, and then x1 and x2 are going to be the eigenvalue, which means if you multiply S times Ci, okay, you get Xi times S. Okay, this is the standard eigenvector-eigenvalue. S is the eigenvector, X is the eigenvalue. So then, I mean, what can we observe about this structure? Okay, so we can observe the following. Then if I add up two matrices that satisfy the previous equation, then what is the eigenvalue of the matrix C1 plus C2? It is going to be x1 plus x2, right? And the eigenvector is still S. And similarly, if I multiply two matrices, I still get a matrix which has eigenvalue x1 times x2 with respect to the same eigenvector S. Okay? So this is very nice. And then like the natural idea that came to the authors of the paper is, you know, we should have C be the ciphertext, S be the secret key, and X be the plaintext. Okay. So if we can do this, it seems this like should be like really helpful to get full homomorphic encryption, because if we want to like do homomorphic addition, just add the matrices. If you want to do homomorphic multiplication, just add multiply the matrices. Right? And then you get like an encryption of the addition or an encryption of the multiplication. It's like a natural idea. I mean, of course, it's not clear how to do this, right? I mean, how do you create this ciphertext? Okay, this we still need to see, but that could be like our objective in order to get FHE, right? However, this is not going to be secure because it's easy to compute eigenvalues and eigenvectors, so it would be easy to compute the plaintext. Okay. Okay, so how to make it work? Well, add the noise. Okay, so like instead of doing S times C equal X times S, add the noise E. Okay, so which means like S times C is approximately equal to X times S plus, you know, some small noise. Okay, and then hopefully, so long as the noise is not too large, say like the max overall entries is like at most Q, right? Then this is gonna be fine. So like everything is gonna work. In particular, you can still decrypt the plaintext. Okay, so but now, I mean, of course, now there is hope that this could work in the sense that maybe we can now actually prove security because we have the noise. At least it's not broken apparently. But now the question is, what happens to the homomorphic operations that we had earlier on, right? I mean, now we added the noise, we need to kind of reevaluate what is going to happen. Well, notice that, so yeah, on the one hand, we have this equation for S1, for C1 and X1, and then the same equation for C2 and X2, right? So this following two equations hold. So now, if I do the addition, which was what I was doing before, like I just add the matrices, what happens? Well, if you do the math, you're going to get the last equation here. So you're going to get that S times the addition of the matrices is equal to the addition of the eigenvalues times XS, which is the eigenvector, plus some noise. Okay. So, and the noise now is different though, right? The initial noise was E1 for C1, E2 for C2, and now the new noise is E1 plus E2. Okay. So, and maybe, you know, like this is actually not too bad because, you know, like if the noise is small, it's gonna grow, but maybe not too much, right? Because, you know, small plus small is still small. Okay? At least intuitively, okay? So maybe this actually is still fine. On the other hand, if we actually do the same, so start from the same equations, now I do the product, right? I do what I was doing before. I'm now gonna do the product. So now you do the math, okay? So if you do the math, you're gonna get the following, that S times the product of the matrices is equal to the product of the plain text times S, which is again eigenvector, eigenvalue, plus something else, okay? And whatever is the something else, you call the noise. Okay, so this is the new noise. Okay, so but now look at this noise, right? I mean, like this noise now grows, and as before, right? We need to say this noise is small. Unfortunately, this is not immediately clear that the noise is going to be small because this ciphertext or this matrix is defined over like ZQ for like a large Q, which means that even if we multiply, when we multiply this matrix with E1, even if E1 is small, the product is not going to be small. Okay? So the noise kind of grows in a way that we cannot control. And then we don't like this because this will completely kill the correctness of the scheme. Okay, so we need to deal with this problem. So how do we deal with this problem? We do it in two ways. Okay, like the first is to actually say, you know, assume that X is just a bit. Okay, so we just encrypt bits, which makes the problem easier. Okay, so X is either 0 or 1. So then when we multiply with the noise, it still remains small. Okay, so X1 times E2 is small. So, but then we need to do something about the other term, this E1 times E2. And the idea is like to kind of like take this ciphertext and use like a binary decomposition, like represent it in a way that it's equivalent, but the entries are small. Okay, so in fact, think of the ciphertext as being like this. Say the Q is 8, then the ciphertext is like 3, 5, 1, 4, and then I do the binary decomposition, which means 3 is 0, 1, 1, 1 is 0, 0, 1, 5 is 1, 0, 1, and 4 is 1, 0, 0. Okay, so I just put it on this new matrix, and then I get a new matrix which I call bits of C, which is the binary decomposition of the original matrix C. Okay, so what is nice about this bits of C matrix? Well, is the fact that the entries are small. Okay, so if bits of C would be here instead of C, that would be good because now the noise would be kind of small. Okay, and moreover, notice that you can invert this thing. Okay, like so how do you go from the binary decomposition of C to the original C? Well, you know, you just need to like multiply with the successive powers of 2 such that you can reconstruct the actual value mod Q, right? So you can do this by publishing like a public matrix which contains all these powers of 2 in the right positions, and then if you do the multiplication, you get C back, right? So because this matrix is usually called G, and because this is the inverse operation of the binary decomposition, abusing notation, this binary decomposition is called G inverse. Okay, so but it's not the inverse of the matrix, right? It's just like a compact way to remember that you know, if you do G times G inverse of C, you get C. Okay? So what G inverse is actually the binary decomposition. Okay, so in particular, if you do S times C, this is equal to S times G inverse of C. Okay. Okay, so then now we are ready to actually give the full scheme. Okay, so this is now allows us to give the full scheme. So the full scheme is going to work as follows. The public key is going to be the LWE matrix A, such that S times A is equal to the noise, right? And what is the encryption of X? Well, the encryption of X will work like this. You take a random R, which is a binary vector, but binary matrix, and then you multiply A with R, okay? Plus you add this X times G, where X is a single bit, and G is the gadget matrix from the previous slide, the one with the powers of 2. Then you take the result mod Q, okay? A times R plus X times G mod Q. So why does it work? Well, first of all, notice that we have almost this invariant that we wanted at the beginning. Right? So what is S times C? Now, if you compute S times C, well, you will get S times A times R, right? As the first part. And S times A is this noise eta, right? S times A is eta, right? And then you multiply with R, right? And eta times R is what I call E. Okay, and because the matrix R is binary, when I multiply eta with R, I get a vector E which has like a small noise. Right? Only like, in fact, the infinite norm would be like something like n times n. Okay, so then S times C is equal to E plus X times S times G, right? Which is essentially this approximate eigenvalue eigenvector relation that we had before. The only difference is that there is G. Okay, only difference is that there is G. And yeah, so then how do you decrypt? It's actually very easy to decrypt. What you do to decrypt is just to compute S times C times the G inverse of this vector, which has like all zeros, and it ends with minus Q alpha. Okay. And the reason why this works is actually very easy to see if you work out the math. The reason why it works is because remember that this vector S has -1 at the last entry, right? So when you do this product, essentially what you get is like something that satisfies the following. If X was 0, it will be something very close to Q alpha. Sorry, it will, yeah, no, sorry. Yeah, if X was 0, it will get something that is very close to 0. And if X is 1, it will get something that is actually very close to Q alpha. Okay, so as long as like the noise is not too large, you never mix up 0 with 1 and vice versa. Okay, so the noise should be like if like so what you do is like you just like compute this value and then you compare it with some thresholds. For instance, this threshold could be like Q by 4, and then the probability that you mix up 0 and 1, you can prove it's very, very small. Okay, so yeah, let me tell you how to do the homomorphism now. So to do the homomorphism, well, you just do like essentially what we were doing before. Okay, so like for instance, you can see very easily that the addition still works. The problem was with the multiplication, right? Remember, before we did C1 times C2, and then the noise was growing in an uncontrolled manner. And now instead of doing C1 times C2, we do something slightly different. We do C1 times G inverse of C2, okay, the binary decomposition of C2. And now if you work out the math, if you do this S times C1 times G inverse of C2, and you do the computation, you get at the end your invariant. In particular, you get like x1, x2 times S times G, which is exactly the invariant that we want, plus the noise, okay? And the interesting thing is that you see like the noise is in the previous row. It is x1 times a2, this was also before, and x1 is 0 or 1, so this is small. And on the other end, you get E1 times the binary decomposition of C2. Right? So like now, instead of having C2, we have the binary decomposition of C2, which is what we wanted, because now these entries of this matrix are small, and you multiply with small, it's like something small. Okay, so you can now actually control, you can control like the way the noise grows. And in particular, like you take like any circuit now, okay? So take any circuit which has like depth tau. And what do? You start by encrypting the input of the circuit, bit by bit. I encrypt the first bit, second bit, third bit, up to the last bit. And now, because you can do like addition and multiplication, essentially like you can also do negation, you can do it like all circuits. So you start with the first, the input, right, which has like very low noise, very low, the minimum noise. Okay, and then you start computing, right, and you compute until you get to the outputs. Okay, and I mean the worst case is that all these gates are like multiplication gates where the noise grows more, and then essentially like for each of them you like pay like some noise. But now you can control this, right? Because you know what is the maximum price that you need to pay for the noise, And you know that if the noise is not too large, then the correctness still hold, and you will never decrypt 0 with 1 and 1 with 0. Okay, so like this is the reason why this scheme only achieves bounded depth. Okay, and I mean, from the point of view of the security, I mean, I'm gonna actually skip this. So like you can prove that the scheme is secure by essentially like using similar techniques how to prove a security of public key encryption from LWE. Okay, as usual for fully homomorphic encryption, the really hard thing is to actually get full homomorphism. Once you get that, the proof of CPA security is kind of like not very hard. Okay, so like then let me tell you like the last kind of cool concept, which is how do we to increase the homomorphic capacity. Okay, so once we have a scheme that works for a certain depth, the problem is that yeah, this works, but you need to fix the depth in advance. Okay, and in particular, everything could depend on this depth, right? So the only way to compute more complex circuits is to fix the depth to be larger, which also incurs in like larger ciphertext, larger parameters. And then Gentry already in his initial paper actually came up with an idea how to break this dependency. And the main idea is this, okay? Like kind of think of the circuit as being like made of several layers. And now you do some computation, right? That when you do these computations, the noise grows. And then you switch the key and kind of like bring the noise back to 0. Okay. So like, again, do some computations, switch key. Okay. So we would like to have a way to, you know, like start with some key, do some computations, switch key, do some computations, switch key. Okay. So that the noise can be controlled in every level. And now we can keep going forever, maybe. All right. So that would be kind of the idea. Still not clear how to realize it, but that would be the idea. So how do you switch the keys, okay? And the idea is actually very simple, and it comes from this perspective on the decryption circuit. Right? So what you think of the decryption circuit, right? So you can think of it in two ways. One way is you have the circuit with the secret key hardwired, okay? It's fixed, and then it takes as input a ciphertext and outputs X, the plaintext. On the other hand, you can think of the same function, same circuit, but with the ciphertext hardwired, and then SK is the input and X is the output. Right? The two things are the same. And the idea is to look at the right perspective, okay? This dual view, where the ciphertext is fixed and the secret key is the input, okay? So then I can do the following. Like, I want to switch key, remember, right? So in order to switch key, so like say, like for instance, in this picture, I want to go from PK1 SK1 to PK2 SK2, right? So what do? I publish some auxiliary information that can be public completely and allows me to go from one key to the other. And what is this public information? It's an encryption of the old secret key SK1 under the new public key PK2. Okay, so I encrypt SK1 with the public key PK2. So why this is useful? Because of this dual view of the decryption circuit. Okay, because then you see, like I have this encryption of the old key under the new key. Okay, encryption of SK under PK prime. And then I run now the fully homomorphic evaluation under key PK prime on the decryption circuit, right? This circuit here. If I do that, what do I get? I get an encryption of the function applied to the input, which is the secret key. So what do I get? I get an encryption of X under PK prime. So I switch the key. So I started from an encryption of X under PK, which was C, right? C is an encryption of X under PK. And now I get an encryption of X under PK prime by doing this switch operation, okay? So essentially, in order to do the switch, what do I need to do? I need to evaluate homomorphically the decryption circuit. If I can evaluate homomorphically the decryption circuit, by publishing this additional information, I can do the switch. Okay, so now, unfortunately, of course, only switching the key is useless, right? I mean, if I can just like switch the key, what for? Then what do I do? Of course, this doesn't suffice, right? I mean, I need to switch the key and also evaluate at least one gate. Because if I just switch the key, I never compute. Just switch key, but never compute. That's not good. I want to compute, switch key, compute, right? So, and that's exactly what Gentry proposes, right? Like he says that a fully homomorphic encryption scheme is bootstrappable if homomorphically you can do this, like change key, do one gate, change key, do one gate, which is exactly what is written in the slide. And and then he proves that that if you have such a bootstrappable homomorphic encryption that allows for a fully homomorphic evaluation of this decryption circuit plus one gate, then you can go from leveled homomorphic encryption to an homomorphic encryption scheme where the ciphertext is compact and only the length of the public key grows with the depth. Okay, because you still need to publish this thing, right? What I said, like to go to one layer to the next, you need to publish an encryption of the old secret key under the new public key. Okay, so for every level, you need to publish this thing. So the ciphertext is very compact now, but the public key is still large. So it's not yet fully homomorphic. Okay? And then the last thing is like, this is what I said, like at the beginning, if you want to get it fully homomorphic, never actually just, never change the key. But instead of like changing the key, use a single key pair and publish an encryption of the secret key under the public key, the same public key. Okay, and this allows for everything to work because now you can compute, and then instead of switching key, you just keep the same key, but you bring the level noise to minimum, or like to a level that allows you to compute another gate. Compute a gate, put the noise back to minimum, compute a gate, put the noise back to minimum. The only issue is that now you need to publish this encryption of the secret key under the public key. And this actually is not known to be something that you can do in general. Okay, so there are encryption schemes that become completely broken if you do this. Okay, if you publish an encryption of the secret key under the public key. And this is called indeed circular security. And if you assume this assumption to be true, which is, for instance, believed to be true for the GSW scheme, then you can actually get a fully homomorphic encryption scheme under the LWE assumption. Okay, and with this, I'd like to conclude my talk. Thank you very much for listening.